Welcome to Breaking Dimension.
So my name is Franz Vollenweider. I'm coming from Zürich, from the Burghölzli. It's a famous hospital in psychedelic research since the 50s. And I'm a member of the Heffter Research Center of the US, which was founded by Dave Nichols to put forward this kind of research. Now in Zürich we have an own center, a Heffter Center, since about 15 years, which I had, and I founded a new enterprise. It's called Swiss Neuromatrix Foundation for the Study of Consciousness. So this is our hospital, and we have three famous children. One was Bleuler, who coined the term schizophrenia. The other was Carl Gustav Jung, the psychologist, and the third was LSD. So there's also a huge research team behind all what I got to present today, and I don't want to thank everybody, but some people that were important for the brain imaging staff was Felix Hasler, Philip Chomor, Michael Committer is running a EEG lab and doing a lot of brain mapping, and Eric Studer is doing a lot of statistics, and we have Gary Schmidt, who's an American, originally a quantum physicist, who started with modeling of brain states from a mathematical point of view, which I will hardly go into today. So the history of our hospital is long, and it started in about 1984 as Hoffman brought in the LSD to the clinic, and we had already tested other compounds that were not psychedelics, but he had developed a number of compounds that activate blood flow and were used to enhance cognition. So the whole story started about here with Stoll and Hoffman, and LSD was studied first in patients. They had very crazy ideas, and schizophrenics, and then they lighted up and started to study depressed patients, and it was much more successful. Some years later, hydroxy-LSD came in, and then in the 60s, psilocybin. But we also had a lot of other drugs, so we studied like psilocybin derivatives, massimol from the flag agaric mushrooms here, was discovered in Zurich. Then we did a lot with mescaline, DMT, psilocybin, THC, and other drugs. So I joined the lab in 1990, and it was the area where the brain scanning came in and all the neuroscience. So I pushed a number of people together to establish a new approach to psychedelics through the modern neurosciences and using brain imaging, brain mapping, neuropsychological things. So then we brought in the Heffter Center, which was an arm of the American Center, but the difference is the American Center is a virtual center, and here we have a lab and the staff. And now the new center is the Swiss Neuromatrix Center, which wants to foster and to focus more on new drugs. So, what are the technologies we use? We use a lot of different technologies, like already told you a little bit, the brain scanning, but we also go down to the molecular level. So, we look at the system and we try to understand how these drugs modify brain activity, the integration of different brain areas, how they are changed under these drugs, how they alter subconscious processing, and so on. But we also want to know much more about molecular interactions of psychedelics with the brain to understand what's the real key mechanism. What can we learn from this, and how could we modify drugs that even may be better and more tailored to certain clinical questions we have to use these drugs in patients. So there are two main things we do. We do looking for neural correlates of all the states, the phenomenology, but we also do, as I said, a lot of new things like neurochemistry, and then some people in the group, they studied relation to meditation or natural occurring psychosis, near-death experiences, and so on. So how does it look from a practical point of view? For instance, here with psilocybin, we give the drug, we give different doses repeatedly in the same subject, depending on the study design. We use drug naives, we use drug users, sporadic users. Depends always on the questions we have in the experiment. And then we have different windows, like for instance, acute states we want to study, post-acutes, or maybe some days later, or even we follow everybody after 3, 6, and 18 months, and we investigate them again. How did, for instance, behavior change due to these drug experiments, and so on. We try to keep the experiments very short. We do one experiment, mostly with one person at a certain time point, and then he has free time to go into arts or listen to music or doing things he likes to do. And we try to do as little as possible in real labs. Most is done in a special new department, which is out of the hospital. It's a research department in the green with a little park, and people even can go out for a walk with some of the people who are responsible for this particular experiment. So I want to start with an idea that Dietrich brought up in the 70s in our institute. He said different inducers can bring you in different into all the states, for instance, meditation or drugs or sensory deprivation or sensory stimulation. And he did a big study with about 400 people using all these different techniques, and this was a controlled study. He started doing one of the first placebo-controlled studies in the 70s and ended up 85 with a huge overview, and he found and said, oh, there are kind of 5 dimensions. One is this oceanic boundlessness, goes into a mystical rapture or mystical state of oneness and unity. It can go the other way around sometimes. It's more an ego dissolution and thought disorder, similar to psychosis in patients. But it can also be much more visionary or more auditory alteration. This is strange dimensions that came out and was not coupled into did not project into the other dimensions, and some basic vigilance reduction or alterations, or sometimes also arousal. So he had this 5-dimensional concept of basically what I was interested in was this oceanic boundlessness, this ego dissolution, feeling of unities, versus this, the bad guy. People always think it makes you psychotic. It can be, you will see, but it must not. And the visionary state. So we had, the first question we had, can we approach this construct based on psychological measures, as Dietrich started to do, and can we also map it out and have some evidence to convince mainstream science yes, there is something in these states that needs to be studied. So we did a huge study, a huge overview. We just published that. If you are interested, you can download everything from the homepage, about 100 papers. You see, we put in about 300 psilocybin subjects on the different doses, and they had to come several times versus placebo, ketamines, MDMA, and so on. This is a study overview about 600 subjects to tease out the common denominator of altered states. So the new dimensions we found by many mathematical tricks and approaches is that we have now a description, at least for research purpose, who brings us or gives us 11 dimensions. One is noetic consciousness, deep positive mood, feeling of unity, disembodiment up to out of body, change meaning of percepts, synesthesias, visual alterations, and then some dimensions that are more linked to the pathological view of these states, anxiety, together with disturbance of cognition, like a breakdown, and altered acoustic alterations. These three together may be similar like first-break schizophrenics. You will see that only about in our whole experimental sets we have done over the last 20 years, we have about 4 to 8% of people who suffer this for a certain time, transiently during tripping. Mostly, we bring people very nicely through this, sometimes really exciting and ordinary states. So with this new map, we can map out the doses. It's like a map. You can use the different dimensions. Here's the intensity. And we can characterize drugs, not only psilocybin and ketamines. Here, for instance, ketamine, different doses. So here, psilocybin. Or quite another map is MDMA. We see MDMA is basically a blissful state. Some changes in body experience. Some changes in blissful and insight, but it's quite different from a psychedelic state. It's just to show this graphically. So, what I was more interested in was one question. Many of the subjects said, we don't have any visual stuff. We don't have illusions, hallucinations, or whatever you label that. You have no visions, but we have traumatic changes in emotion, in being united with the universe, and so on. And that brought us another question. Can we have subpopulations that are different? And what you see here is three main types we found over many hundred trials, controlled trials. We had a type that they had almost no oceanic boundlessness, that's some anxiety, no visionary restructuralization. But another type was very into this oceanic boundlessness, and in a visionary state, but nothing with anxiety. And the other type was the other, maybe the heaven guy, the guy in heaven, only mostly oceanic boundaries, but no anxiety, no visionary states. So this is a kind of typology. But what is interesting, if you look at this, that the rate of anxiety was only 8% in some 100 subjects, depending how the setting is and how you teach them and how you prepare these guys for these experiments. That brings us to a very important questions for using research subjects. Are there any predictors for these states? And Dietrich started with that, and just show a few: optimistic extroversion, high aesthetic sensibility, non-dogmatic religiosity are very fostering positive oceanic boundlessness together with the dose and the setting. Other predictors like emotional lability and rigid conventionality, these subjects are going rather into an anxious state. So it's in normal subjects, it's not what we use for patients. It's very important to get some indications how can we prepare the subjects. But nowadays, as you know, the mainstream goes into molecular biology, and certainly we have genotyped all these subjects we have investigated in the last 4 or 5 years, but we haven't done a lot of analysis yet. But we found some polymorphism in a serotonin receptor 2A receptor, and these people, they cannot filter down external information, sensory input like normal people. They have a reduction in so-called sensory gating. These are these people with this kind of genes, and these are the normal people who can reduce sound or visionary input, but these people are hampered in doing that. So these people dramatically respond to psychedelics. So this is a new avenue which I do not want to go in. We have now about 20 SNPs where we can show, okay, genetics has a traumatic input on, or traumatic modulation on personality traits and psychedelic experience. So now let's go a little bit to the brain. The brain is very highly complex. There are about 100 million neurons, 10 of 9 neurons, and each neuron has about projections about 10,000 others. So to understand this is a little hard, and we don't have any idea how it really works, but we have approaches to study population of neurons or how different brain areas work together. We have rough methods, we have more refined methods, and we have nowadays also quite nice methods. So one approach is this scanning, which you have heard from Robin yesterday or this morning. And we have put people in a scanner with one question. We put the same subject twice, different doses, with ketamine versus psilocybin, to tease out the common patterns. And what you see without being a scientist, that you find with that method at that time overlaps between ketamine, frontal activation, and psilocybin, frontal anterior cingulate activation in the posterior regions and in the thalamus. So these were measurements done, people in the peak experience with relatively high drugs, 20 milligrams psilocybin to 24, and ketamine about 80 milligrams per hour. So the question was, okay, when they go in this kind of end path, so they go into the trip, that's a lot of adaptation in the brain. It's not like that in the beginning. There's tremendous going on. So this is what they experience in a certain state. And here we mapped the psychology to this state, and you see it, frontal activation and some deactivations in deeper regions is linked to this state when they are in this oceanic boundlessness state, this OB. But when they are frightened, they have more anxiety, we found mostly a decrease in frontal areas and an increase in the thalamus. This is just one possibility where people can be in. Another more interesting mapping was the being out of body. With ketamine, you can mimic that. So certain circumscribed deactivation with ketamine in the parietal cortex and some deactivation in the thalamus. You close the sensory gates for the input to the cortex is blocked through shutting down the thalamus, and some areas shut down. So in that activity pattern corresponds with this disembodiment about also some were out of body, but not all. If you take patients, and a colleague of ours in Lausanne has done that, he mapped patients that always have this feeling of being out of body, seeing themselves. They exactly have in this brain area this deactivation. Why is it like that? I don't want to think about it now, but just to make a parallel, that these drugs can you bring in a very circumscribed state. Another very important thing is illusions. Should move a little bit. Illusions is if something is not stable and you are experienced enough to know what an illusion is. More interesting are hallucinations or vision. So that means you have no sensory input, and we sometimes shield the eyes of our subjects and do then all the experiments. So have the eyes closed, and nevertheless they have their inner world and activation. So what's interesting in terms of visionary experience, when a signal is coming through the eye, through the thalamus, through the primary visual cortex, then this is the first area in the brain where vision is processed. There are cells here, this corresponds, this part of the brain to this, that only detect contrast or brightness. Other cells conduct movements, other funny faces, and so on. So different cells detect features, but these features have to be brought together to a whole, and we think that the frontal cortex, the newest and the biggest part in the human brain, makes a whole of all these different processes. So this is the so-called binding problem. Individual information has been or has to be synthesized into a whole and been integrated. So you can now map out what is psilocybin doing in all this network. Is there some disturbances in an area which is responsible for movement or for brightness and so on? To have some clues about how these drugs may produce vision. So what we found, maybe you cannot see it really, is a shutdown from some areas that are responsible for integration of external and internal visual information, and also for movement and brightness. These are corresponding, these dots here, to these areas. So this is a very static thing. When you do this brain scanning, and you have to measure for 4 seconds, it is quite a long time. So we went on to look at the real spatiotemporal dynamics, and that means you're using different EEG brain mapping technologies, and you give a signal, for instance, to the eye, a stimulus, and then you measure continuously the brain activity. It's always active. And you get maps. Here is the time, and here is the activity. It goes up, then it goes down, and it's finished. And the whole process goes about a third of a sec, 300 millisec, if you give a signal. Now you can go and back project this information onto a brain, and you get maps like with fMRI scanners from the surfaces on how these areas are working together. So it's a tremendous amount of information. So we measure, or we shoot, about 1,000 images per second. So every millisecond, we know the brain is in that state. So vision is a constructive process. Everybody has his world, everybody has his consciousness, but there's no real thing behind it. You construct the world, you use your brain for this, and it does not mean that this gives rise to consciousness, but it means that you need the brain to have a picture, an inner image of the world. So here, for instance, very simple experiment. There's a Canisa figure, and you see here lines that do not exist. It's a little, if you would dim the light a little more, you have here a triangle. But there are no lines here, so it has to be constructed. So it's, even if you go to faces, it's even more complex. But take a simple experiment here. You look at the spatial temporal dynamics. You take a volunteer, you have here the eye, you give such on the screen such a figure, and you can look how is it processed, where is it processed, and so on. So you get out within a second how the brain areas process the signal. Here you show the figure. This has to be completed. This object completion has to be done, and here is the time. And you see, after 100 milliseconds, something is going on in a certain brain area. Then there's a deflection, and it goes on, and the figure is processed. Interestingly, after 170 milliseconds. If you switch this, what we do on the computer very fast, and he sees this or something in between, you see complete different wave. And now we see the difference between this figure, Canisa and non-Canisa figure, is processed. The completion of the contour is here. Now we project that back on the brain. We do that several times. We take the psilocybin or placebo. We do this 300 times. And we get out the brain areas that process this whole object completion. What we found is that psilocybin modifies the difference between a Canisa and non-Canisa figure. And the higher it goes, the more these areas shut down. So that means the external world is not that important anymore. So the brain focuses on internal processing. The other thing what is interesting is that areas that are responsible for contrasts get enhanced in their processing and brightness. But the construction of this illusionary contour, it's an illusionary contour, such a Canisa figure, is reduced, and this area has less readout from the frontal cortex, who integrates the whole information. So that means top-down, there's another kind of controlling incoming sensory information. Here, what's going on then? This area is less processing external information, and this gives room to the internal production of vision. The more the area is reduced here, the activity, the more people hallucinate, or you can label it visionary state, or the more the brain takes information from the memory or whatsoever and gives room for an inner experience. So you shut down the normal world. Now you can see here on this a little bit how it's just a third of a second, how the 300 millisecond brain areas interact to produce then hallucinatory states, and the information goes to the frontal cortex, just as what we can do now. Another interesting thing is perceptual binocular rivalry. You see this vase or you see the face. Your brain cannot see both at the same time slot. So you see alternately face or vase. So if a neuron is coupled to another, sometimes they are in phase, they are oscillating, and this is also a kind of oscillation. Everybody has his own switching rate. Normally it switches every half of a second. In some people, every second, sometimes 1.2 seconds, and so on. We do much more complex binocular rivalry testing with subjects to look how is this switching. And this switching you cannot influence. Your brain, let's say, automatically is doing that. And we were asking, does psilocybin interfere with this automatic thing? Is it changing a kind of coherent oscillating? And what we found is that not on a trip, if you have the switching rate, if you give psilocybin to a normal volunteer, the brain comes into, it gets tuned. It goes in a very stable frequency, and people who have, this is one subject has this kind of frequency distribution of switching, gets very, very, very tuned. And the more he is over the peak, it's after the peak experience of psilocybin, it goes into the phase where it gets more absorbed, where it's more a meditative state. So we have done that with normal subjects, and we went to India. Here's some of these guys, and they were very helpful, doing the same without psilocybin. You see, they can do that. They can go and tune their brain in a very organized state. And interestingly, some of them, not from the Dalai Lama, took psilocybin in Switzerland and said, you really don't need it. We are in that state. It's very interesting. Okay, another 5 minutes, that's fine. This is was a little bit how we studied the whole system, or the system temporal dynamics, to become more closer what's really going on, how these drugs modify the brain, and how the brain produces or constructs or perceives this conscious state. So what is interesting for the future of psychedelic is how do they work. And you may have heard these two nerves communicate through synapses. This is a nerve ending, and this is the next synapse, postsynaptic membrane. And in this membrane, there are proteins. There's like something like this. There's a three-dimensional structure. And a molecule like psilocybin is very similar to serotonin. It's very, very little different. Hooks up in the receptor and goes into the receptor and modifies the three-dimensional stereochemically organization of the receptor. It's very dynamic. There's no chemical reaction. It's just like a magnet. It goes in, pushes a little bit. There's a protein. It wobbles a little bit, and the signal gets produced from this going into the receptor. And here a lot of things goes on. So the difficulty is we have a number of serotonin receptors. We have at least 12. And we had a lot, it took us a lot of time to block the right one. And we showed more than 10 years ago, if we block the 2A receptor, there's a 2A, B, C, there's 5-HT7, 3. If we block this, we block the whole psychedelic experience. That means this receptor is really important. Drugs that interfere with this are psychedelic-like, and these drugs are mescaline, LSD, and psilocybin as standards, and DMT. DMT is very short-acting. Now, the problem is, if you do that, you give the drug, after a few minutes, the receptor gets down-modulated. It goes into the membrane, and you can take more and more of the drugs, but it has not that effect anymore because you get a kind of tolerance. The next day is a little bit better, but still you're tolerant. So you have to wait for 3-4 days to have full action. The other thing is that most of these drugs, like LSD and psilocybin, also hit somehow this receptor, the 1A. It also has some effects, and we wanted to know what are all these contributions. Now, this was hitting such a receptor from outside, but what we know now since then is we have hundreds of internal mechanisms that gets turned on through psilocybin. And it's much more interesting to look at this now. We have all the molecular techniques. So let's take the 2A receptor, and what we see is that all psychedelics activate within the cell EGR1 and 2. It's DOI, DOM, DOB, mescaline, LSD, and psilocybin. But the non-psychedelic 2A agonists, they are molecules that activate the receptors. These molecules are very important for regulation of blood flow and the vessels. They are not hallucinogenic, but they also activate a lot of things in the cells, but this is not important. We found only the psychedelics activate the red fields here, these two early genes. And early genes start to activate the brain and start to induce, for instance, plasticity. It's exactly what we've, oops, sorry. Wow. Oh, that was the wrong button. So, we are here again. What's going on now is that by understanding these receptors and all these subreceptors, we can make new molecules. For instance, here one compound works similar like LSD or psilocybin, hits the 2A receptor, but also hits the 1A much more. And what we get out of this is the normal psilocybin effect. We have a compound, he's less visual, but he has all the qualities of psilocybin. Here we modified 6 LSD-like molecules. We don't want to go into chemistry. They, for instance, they give you all the euphoria, they give you the visual effects, but they give you less anxiety and so on. That's the trick why we want to study all these little details, which you may think, oh, these are not so important. But the newest story out of that is, and this is very important for clinical practice, as I said, all the psychedelics hits the 2A, hit the 1A. Molecules like this one that hits the 1A much more are less visionary, but they are still tactogen, or they bring you into a kind of oceanic boundlessness state. But what's the newest story of all the psychedelic research is the most fascinating is that this receptor, and we know this since 2 years, is hooked up to another receptor, and if you shut down this, you shut down the psychedelic experience, but if you activate this, you have the psychedelic experience back. That means we have a new avenue now that we can go into the cells, modify this activity, and they are very new compounds. They all have numbers because we don't, you cannot buy them yet, but if you give it a normal subject, you can play with the psychedelic state. You can turn it on, turn it off, you can modify it. So that's a little bit the direction where we go. And the perspective is that these new molecules, they modify the neural plasticity, which is very important for learning, for healing, and they have no real dramatic effect, but they facilitate that you are open and that your chain can adapt to new behavior. So thank you very much for your attention.